In our first regular video, I think it's a good point to start is to talk about how do we measure angles. And before I do that though, I looked up Hipparchus, who I mentioned in my introductory video. Hipparchus, the father of trigonometry, was born in 190 BC and died in 120 BC. So he's actually, I think, came along quite a bit after Euclid. Probably. I'm not sure Euclid's dates. I have to look him up too. But anyway, so trigonometry goes back a little over 2,000 years, you might say. The initial study of the relation between angles and triangles. Alright, so now then, let's talk about how we measure angles. And there are at least three ways to do it. There might be a fourth one called Mills, but I'm a little fuzzy about that one, if it exists. The obvious one everybody knows is degrees. We also, very importantly, measure angles in radians. And then a third way is, I think the civil engineers sometimes use gradians. Radian with a G. And I'll tell you about that. But basically, we're going to study angles in degrees and in radians. And so let's go with the familiar one, angles in degrees. And everybody knows that a circle is divided into 360 degrees. Is a full circle. I think everybody knows that just about. Where'd that come from? Okay. Well, you have to blame the Babylonians for this. The ancient Babylonians. They use a base 60 counting system. Now, we use base 10 because we have 10 fingers. And virtually every culture in the world uses base 10. And so we have digits from 1 to 9. Then when we get past 9, we introduce two digits, 1, 0. That's 10. So actually the basis for our number system when we count is powers of 10. I think there are a few primitive tribes around the world who about the only numbers they have are 1, 2, and 3. Okay, anything over that is just many. So you might say, hey Joe, how many kids do you have? I have many. All right, well, to me, having more than 3 kids would be many kids. And so there's, I don't know. Anyway, everybody else uses base 10. But in ancient times, the Babylonians liked the number 60. And base 60 is actually has a name. We call it a sexagesimal system. Rather decimal. Sexagesimal. 60, base 60, basically. And we look at the numbers that can divide into 60. 1 can divide into 60, so can 2, 3, 4, 5, 6, let's see, 8, 9, 10, 12, 15, 20, 30, and 60. Alright, a lot of numbers can be divided easily into 60. As compared to 10, the only thing that divides into 10 is 1, 2, 5, and 10. Anyway, if you ignore the 1 and the 60, there are, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Unless I forgot something, there are 10 numbers between 1 and 60 that can divide easily into 60. Whereas with 10, we only have 2 and 5, 2 numbers. So it made fractions pretty nice in their day, because they didn't have decimals. No decimal points, no decimal places. And decimal places, I looked it up briefly. There's to me, no clear start for decimal numbers. It kind of evolved. First, someone had to create 0, and a symbol for 0. The ancient Greeks didn't have a 0. And so various cultures around the world, Chinese, the Egyptians, the Hindu-Arabic system, they came up with zeros, and eventually they created the decimal system, decimal numeration. So you could write in decimals. And so all that took a long time. It didn't really filter over to Europe until the 1200s. And so I think in the 1200s, Europe was very backwards in mathematics. They were still using Roman numerals. If you ever tried multiplying and dividing Roman numerals, you know it's about impossible. And so, anyway, Babylonian base 60 is why we have 24 hours in a day. See, 24 is 2/5 of 60. It's a nice fraction, 2/5. Every hour is divided into 60 minutes. Every minute is divided into 60 seconds. So that's all a hallmark of the Babylonians, including 360 degrees. Now, what else? What else do we do with that? Well, a degree can be subdivided into minutes. So 1 degree is 60 minutes. So let me write minutes here. Everybody knows the degree mark, right? All right, now here's what's really important. Particularly if you're taking me for a class, I'm going to come down hard if you forget to write the little degree mark. Because 1 degree is a small, tiny chunk of this circle, an angle. It's 1/360th of a circle. Number 1, if you forget to write the degree mark, the number 1 is interpreted as radians, and it's around 57 degrees. Technically, it's 180 divided by pi degrees. So it's around 57 some degrees. So, big difference there. Always write the degree marks. Okay, if you mean degrees. Got to write that degree mark. It's very important. Because if you want minutes, you have to write this little apostrophe symbol. 60 minutes is 1 degree. And we also divide minutes into seconds. So 1 minute is 60 seconds. So 2 of those in this context means seconds. There we go. So that's a lot of division of a circle or angles into very small parts, and it's still used. I'll tell you a quick story. In around 1990, I received some junk mail with a ballpoint pen inside, and when I opened it up, the ballpoint pen had one of those things where you scratch the stuff off and you get something. And this was a little sweepstakes prize. So I scratched the stuff off with a nickel, compared my number on my pen with the letter, and I won first place. Oh wow, was that exciting. So I thought, well, what is first place? Well, grand prize first place was like $100,000. I said, oh. Then they had a second first place, $20,000 in gold coins. So well, I would settle for that. And then they had 30 first place prizes, which was a piece of property in Mexico at a resort area up in Baja, California. Okay, so naturally I sent it in, naturally I got the piece of property. So what did I win? I won a deed. I owned property for 30 years, and the property was in, Baja, California. It comes down like this, and here's up here. Okay, here's like San Diego and Tijuana and so forth. Up here, some rich Americans, Canadians had developed a little resort down there, and I had a piece of property that was 5,000 square feet in size. Oops. That's supposed to be 2 square feet. All right, 5,000 square feet. And I said, well, that's not very big. How big is 5,000 square feet? Well, let's look at that. All right, this is math, right? We can do math problems. So, if you had a square piece of property that was 5,000 square feet, if it's square, that means the area would be the square of the sides, x squared. X squared would be 5,000. And so x, take the square root of 5,000, it's around about 70.7 feet. So I had one property about 71 feet on the side, somewhere in Mexico, and Mexican government only allows foreigners to own property for 30 years, and then it goes back to Mexico. And so, oh, well, that's great. Now, why am I telling this story? I think it's a great story because it ties in with degrees, minutes, and seconds. And so by the way, I never visited it. I offered to people, look, hey, if you want to go down and camp out on my little piece of beach property, go for it. I'll give you the coordinates. And basically, they tried to get me to subscribe to some newsletter, which I had to pay for, about updates to the resort down there. I thought, keep it. All right, so I had this little small piece of property. Now here I'm coming to the punchline. The legal document I got from lawyers in San Diego gave coordinates that this was property number such and such on a larger piece of land. So there's a piece of land that had coordinates given in degrees, latitude and longitude. Latitude and longitude. And I'm just making up numbers because I've lost that document. But let's say that the latitude, longitude. Let's say the longitude, again I'm making up numbers, was 114 degrees, 37 minutes and 14.2679 seconds. Okay, so I had 8 numbers, 2 each for each corner, latitude and longitude, in degrees, minutes, and seconds. And what really amused me is that the seconds went down to 4 decimal places. So, wow, those guys are good at surveying down there. And because when you find out how big 1/10,000th of a second, arcsecond, is on the face of the Earth, it's pretty tiny. It's pretty tiny. And so, so I was really puzzled by all this. Like, okay, well, one thing is that people still use degrees, minutes, and seconds. And they, but to that degree of accuracy, it's kind of funny. Anyway, I worked at this problem, and what I finally figured out, on the surface of the Earth, this area, and my property was, had a number on it, it's somewhere in there. This area was exactly 1 square kilometer. Well, of course, the Mexicans work in the metric system. I had a piece of property that was rather small on 1 square kilometer somewhere in Mexico. And so that was an interesting math problem in itself, trying to figure out that area on a globe, on a sphere that the Earth is, and figure out the area. That was an interesting project for me. Anyway, so now this inspires me to do what I'm going to do next. I'm going to, let's look at the circumference of the Earth. And first of all, I'll talk about how someone figured out the circumference of the Earth 2,000 years ago. And then we'll look at how big is a degree, how big is a minute, how big is a second of arc length along the surface of the Earth. I think it's a great exercise, and eventually we'll talk about how to convert this format, degrees, minutes, and seconds, into a purely decimal format, so you can use your calculator. All right, so let's go on with that. I'm going to erase the board. We'll tackle those problems. I like to connect our study of angles in degrees, minutes, and seconds to the size of the Earth. But first of all, what is the size of the Earth? Did you know someone figured this out with pretty good accuracy around 2,000 years ago? All right, so it's a Greek mathematician, Eratosthenes. I wasn't really sure. I'm not really totally sure if that's how you pronounce it, but that's how I always pronounce it. Eratosthenes was in his day, was the librarian of Alexandria. Now, Alexandria, Egypt, had the greatest library in history. It was eventually burned down by a bunch of looters and robbers and conquerors. But the Library of Alexandria was famous for having a copy of about every book ever written. And in those days, it would have been probably mostly in scroll form, and all hand copied, no printing press. All the books ever written, handwritten copies, and a huge library on the coast of the Mediterranean in northern Egypt. All right, well, Eratosthenes was at one point the librarian there, and but he had roamed the world. He studied mathematics, and he's also famous for something else. Something called the sieve of Eratosthenes was a way he figured out in order to find prime numbers by eliminating non-prime numbers. Very nice thing. If you're interested, look up sieve, S-I-E-V-E, of Eratosthenes. And when I was in, I think, junior high, I took a piece of graph paper which had a gazillion squares, and I figured out all the prime numbers up to 10,000. See, we didn't have calculators when I was in school back then, and so it came in nice to know prime numbers in case I wanted to reduce fractions. And so anyway, I like that. But he also was told his tale one day. Someone came to him and said, "Look, Eratosthenes, down in Aswan, on the first day of spring or first day of fall, I forgot what that's called, something solstice perhaps. Anyway, on the first day of spring or fall, there's a well down there, a deep well, and at noon you can see the sun shining at the bottom of the well. In other words, the sun was directly above the well. And if you put a pole in the ground, the pole would cast no shadow." Well, he thought that was pretty neat. So that came that time of year, and when he put a pole in the ground, it did cast a shadow. The shadow angle, if you look at this angle here, that angle was 7 degrees 12 minutes. He measured it, 7 degrees 12 minutes. So our first challenge is, what in the world does that mean? 7 degrees 12 minutes. Well, because there are 1 degree is 60 minutes, if I divide by 5, I get 12 minutes over here. I get 1/5 a degree, which is, in modern terms, we call that 0.2 degrees. And so 7 degrees 12 minutes is 7.2 degrees. Okay, great. It turns out that's a very handy number. All right, now, so he thought about this and came up with this idea. And so here's the Earth. Now, you know, like most educated people, Eratosthenes believed the Earth was round. And the whole idea that most of the world thought we had a flat Earth, Columbus was going to sail off the edge of the Earth, and if he went too far, most of the educated people didn't believe that. There's too much evidence that we had a round Earth. For example, the moon is round, the sun is round, and why wouldn't we be round? What about spherical? Are we just a disk? Something else? Are we a sphere? Are we a sphere? And some evidence of that, if you watch the ship out at sea, if you can see it quite a bit offshore, in those days, since they're all sailing ships, they might have only seen the top part of the ship. The hull might have been missing, just the top sails. And that's because it's going over the curvature of the Earth. You know, so we had different kinds of ideas there. Also the idea of symmetry. In 3 dimensions, the most symmetric object is a sphere. All right, so Eratosthenes believed we're a sphere, and so now the I think I was did I say the first day of spring? I think I did. I think I meant the first day of summer. All right, so the Earth has little lines here. This is the Tropic of Cancer. Tropic of Cancer, and the one in the southern hemisphere I think is called the Tropic of Capricorn. Anyway, it's around 23 degrees north latitude. And the Tropic of Cancer, and I said first day of spring or summer, I should have said summer. So in the summer, the Earth, because the Earth's tilt as it goes around the sun, on the first day of summer, the sun is bearing down directly overhead on the Tropic of Cancer, which happens to be where Aswan was. The city of Aswan in ancient Egypt is about right on the Tropic of Cancer, and that explained why the sun could be seen in a deep well. A deep well. All right. Well, Alexandria was up here somewhere on the coast of the Mediterranean. I'll abbreviate it, but Alexandria is up here, and we look at the geometry here with the sun shining this way. It's going to create an angle when it pulls in the ground, and the least angle you're going to get is 7 degrees 12 minutes according to Eratosthenes. And so he figured that, well, that angle corresponded to that amount of the curvature of the Earth. In other words, the Earth is spherical, it's round. He knew that. And 7 degrees 12 minutes was a certain north-south distance on Earth. All right, so it works out. So you say, well, look, we're 7 degrees 12 minutes north of Aswan. If we knew the distance between Alexandria and Aswan, we could figure out the full circumference of the Earth. What a brilliant idea. So he hired some pacers. I don't know what they were called in his day, but they were guys that just, you know, they were paid to walk from here to there and measure their steps, and they had a regular pace. And so they were, you know, mildly accurate, I guess. Anyway, he hired off at least one guy, maybe a couple, to pace the distance between Alexandria and Aswan. Now, Alexandria just happened to be due north of Aswan. And came up with 500 miles. So it was 500 miles was the distance between Alexandria and Aswan. And 7.2 degrees is, if you take 360 degrees divided by 7.2 degrees, that ends up being exactly 50. 50. So in other words, this is 1/50th of the circumference of the Earth. So if you multiply 500 miles times 50, you get 25,000 miles. So there we go. Around 2,000 years ago, it was known how big the Earth was. According to Eratosthenes, 25,000 miles in circumference. And you know, that was a very, very good measurement. I mean, it's more than 99% correct. It's the error is less than 1% in reality. Now then, a couple hundred years later, a famous historian named Ptolemy, and there were a lot of Ptolemies in those days in Egypt. Some of the pharaohs were called Ptolemies. Anyway, this Ptolemy was very influential. He wrote books, traveled the earth, traveled the world. He heard about Eratosthenes' experiment and decided to repeat it, and screwed up something. And Ptolemy declared that the Earth is 18,000 miles in circumference. Wow, okay. And, well, he was a lot more influential than Eratosthenes, who was relatively unknown and to the public. And so people believe that. And that's why when Columbus sailed from Europe, landed somewhere in the Caribbean, where did he land? Was it in the Bahamas or somewhere in there? He landed over there. Columbus never made it to the mainland of North America. Never made it to real America, what we call America. But he reached land, and the indigenous people there, he thought, were from India, because by his calculations, he should have been in India. You know, he's missing 7,000 miles. Okay, no one knew there was an extra 7,000 miles between there and India. He was looking for a trade route, lucrative trade route to go to India. So he took the chance going across the ocean. You know why that was a big chance? Because at sea, you can navigate north and south by looking at the positions of stars relative to the North Star, which is kind of fixed up there. So depending on angles of stars, you could figure out where you were, north and south on the Earth. But east and west, a big problem, because the Earth is spinning east to west, or west to east. Which way is it? Anyway, the Earth is spinning. And because the Earth is spinning, the stars are moving targets. So you cannot navigate with stars east to west. That's why in those days, Columbus's day, the ships tended to hug the coast. They didn't want to get too far away from the side of land. But if you just went roaring took off across the Atlantic Ocean, then without sight of land, where are you? You could tell how far you are north and south. East and west is a problem. And what they were missing was a clock, a good clock that you could have on a ship. And that problem wasn't solved until the 1700s. So when the first invention of a clock that would keep good time on a moving ship. So it was guesswork on Columbus's part, and using the best information at his time. Earth was 18,000 miles in circumference. He thought he landed around India. That's why they're called Indians. Okay, that's why our Native Americans were called Indians, and because of that, this mistake, which took a little while to figure out. Eventually, they figured out that hey, we're missing some mileage here, and they went back and recalculated the size of the Earth. All right, so there we go. That's how we do the circumference of the Earth. Now, Let's go from here. Now from here, I want to, my goal was to look at how big is a degree? How big is a minute? How big is a second on the face of the Earth? So let me erase all this and we'll talk about that. My goal is to tie the circumference of the Earth to degrees, minutes, and seconds, just to give you kind of idea of size, and also a little bit of computation with degrees, minutes, and seconds. So I think it's a good exercise. And the first thing we need is circumference. What is circumference? And probably many of you know that circumference is 2 pi times the radius. All right. Now where does that come from? I think you got to know where that comes from. And it's not a mathematical theorem. It's by definition of what pi is. The number pi is by definition the ratio of circumference to diameter. And so every circle, if you measure the circumference and divide by the diameter, you get the number pi, around 3.14. Okay, so it means that algebraically, if you multiply by diameter, circumference is pi times diameter. Now, radius is half of a diameter, so diameter is 2 times radius. So that's why we normally replace d with 2r, and we get circumference is 2 pi times radius. So it comes from the definition of pi. Well, then, what about the Earth? How big is the Earth? Well, Eratosthenes is estimated 25,000 miles. It's actually a bit different from that. The one I like to use, the radius of the Earth, measurement I like to use, the radius of the Earth is, keep you in suspense here. It's about 3,959 miles. Okay, so that means the circumference would be 2 times pi times 3,959 miles. And now that's approximate, and the Earth is not truly round. It's close. It's a little bit flatter at the equator than it is at the poles. It's slightly flattened, and I don't know if you're in space if you could tell that or not, if it's enough to tell. It's flattened because of the rotation of the Earth in the direction of the equator, around the equator. When the Earth was molten, the centrifugal force forced it out slightly, flattened it before it solidified. So it's not quite perfectly round, but it's close enough. And so we'll say, let's use 3959. And let's see, the French, when they came up with the metric system, they decided that if you take the distance from the North Pole down to the equator, they call that 10,000 kilometers, all right, or 10 million meters. So distance through the pavement outside the Cathedral of Notre Dame in Paris. There's a plaque in the ground, I'm told. The distance from the North Pole to the equator is defined to be 10 million meters, or 10,000 kilometers, which meant this circumference is 40,000 kilometers. And let me just use my calculator to work that out in miles. So conversion. My calculator does this stuff pretty nicely. So if I take 40,000, let's see, kilometers and convert it to miles, I get 24,854.8. If I divide by 2 and divide by pi, I get 3,955.8. So 3,900 and around 56 is the circumference through the poles. We said it's a little flatter, so that would be a little smaller. Around the equator, I expect it's probably that. So I don't know if this number, I forgot where I got it from, is around the equator, if it's just some sort of overall average. But it's not off by much, is it? A couple of miles. All right. So let's not split hairs. Circumference of the Earth, if I use that number, and you've got a pi button on your calculator, very handy. Look for pi. Don't punch in the numbers for pi because this has all the decimals you need. Every calculator, scientific calculator, has a pi button. So 2 times pi times 3,959. Let's say this is about 24,875 miles. All right, around that. Now, Eratosthenes got 25,000. So he was off by a tiny bit. You know, when you figure the difference there, it's I don't know, less than, what, 0.5%, something like that. What would it be? All right, I got to do this. If I subtract 25,000 and divide by 24,875, it's around 0.5%. So Eratosthenes, 2,000 years ago, was off only by 0.5%. That's pretty amazing. Pretty amazing. Okay, so if I have, let's just start with 24,875 miles, and I want to, that's the circumference, okay, and I want to know, well, what's a degree of, what would it be? Well, it's just funny because degrees going around this way would be longitudes, right? Longitudes go around the poles. And so the degrees vary because at the equator, the difference in 1 degree longitude is larger than when you go up north. And eventually get to the North Pole, it meets there. And so differences in longitude vary depending on how far north or south you are from the equator. But latitude, your distance north or south, latitude lines go horizontal, and they're all equally spaced. So let's think of this in terms of latitude, going north or south. Going north or south, latitude marks are equally spaced on the sphere. I wish I had a globe with me here, but I don't. All right, so this is one circle. So if I divide by 360 degrees, let's see. So divide by 360 degrees, I get. So I'm just going to use the integer number right here. But from here on, I'm going to use all the decimals of my calculator. By the way, you should be, I entered that wrong. You should have your calculator on you and be doing this yourself. 24,875 divided by 360 is about 69.10 miles per degree. I'll spell out degree. All right. No, I tell you, I changed my mind. I'm going to call this 1 degree, per 1 degree. 1 degree. All right, they'll save some writing. So 69 miles north and south. So if you travel north 69 miles, you've gone approximately 1 degree of latitude on Earth. Great. All right. So how much is that in minutes? Or how much is a minute? All right. So convert to minutes. I know that 1 degree is 60 minutes. So look at this. I multiply by 1 over 60, but specifically it's 1 degree over 60 minutes, and the degrees cancel off, okay, leaving minutes. So using all the decimals in my calculator, I still have 69.09722222222. If I divide by 60, I get 1.15. It's about 1.15 miles per degree. I'm sorry, per minute. So 1 minute of arc is a little over a mile. One minute. All right. So does this number look familiar to you? 1.15. Give me a minute to think about it. That number is used. That distance is used. It's been used for centuries, in fact. Have you thought of it? Well, if you served in the Navy, you would know what that is, I bet. That's 1 knot, nautical miles. So this is 1 nautical mile. All right, so Navies like to use nautical miles because it makes for measurement along the Earth pretty nice. You just use arc minutes or arc seconds or arc degrees, whatever. Nautical miles, and nautical miles per hour are called knots. K-N-O-T. So one knot is 1 nautical mile per hour. Okay, so a little bit different from standard mile. All right, so that's how big a nautical mile is. It's only a little over a mile. All right, now let's convert that to seconds. So I'm going to write down here. I have 1 point, and I carried all the decimals in my calculator because I want the best precision. So I'm not going to round anything off on my calculator yet. 1.15 miles per minute, and I convert to seconds. I get 1 minute is 60 seconds. All right, so I'm going to cancel the minutes and replace them with seconds. And by the way, part of the reason I go through this exercise is I want to introduce you to the idea of dimensional analysis. All right, so I'll have a lot to say about that later on. All right, so 1.15 and all my decimals divided by 60 is about 0.019 miles per second. Now, I don't know how to relate to that, so I'm going to keep that decimal on here. I want to convert it to feet. And how many feet are in a mile? Do you know? If you don't, learn it, because you'll need it for this class. How many feet are in a mile? All right, well, it's 5,280 feet per mile. You see, I'm multiplying by 1. These are equal, aren't they? 5,280 feet is equal to 1 mile. That equals to 1. When you multiply by 1, the values don't change. Well, the numbers change, but the value hasn't changed. So I cross-cancel miles, and I have feet. So whatever that is, divide by 60, and then multiply by 5,280. All right, you should get about 101 feet. So this is about 101.3 feet per second. Arc second. Okay. Did you know the astronomers use arc seconds? You know, the coverage of a telescope in the sky is a certain number of arc seconds. And so you see that rating sometimes. The astronomers will use seconds in their work. All right, so pace off 100 feet, and you've got about 1 second on the surface of the Earth. So it's and do you remember my problem where I won a piece of property in Mexico, and they gave me the latitudes and longitudes down to 1/10,000th, 1/10,000th of a second. Would be about tenth of a foot, which is around an inch. So they is that right? Yeah. If I divide by 10,000, no. Look, if I divide by 10,000, okay, and then multiply by 12, because there are 12 inches in a foot. That's about 0.12 inches, about a little less than 1/8 of an inch. So if I was to believe the latitudes and longitudes given to me by the Mexican government through lawyers in San Diego for me, a recipient of free property in Mexico, I would have to believe that they can survey down to 1/8 of an inch on the surface of the Earth. Pretty amazing, pretty amazing. This was probably well before they used global positioning satellites. 1/8 of an inch, that's amazing. All right, a little unbelievable too. Okay, so there you go, some kind of idea, and so I wanted to get you a little bit used to degrees, minutes, and seconds, and next we're going to learn how to convert between that format and degrees decimal. And I also wanted to begin to introduce to you the idea of dimensional analysis, which we're going to use coming up pretty soon to solve problems. Okay, so let's go on to those conversions.